So now we're going to read each of these sentences which describe a chemical reaction, and we're going to write the word and skeleton equation. So for the first one, we've got propane gas, which has a chemical formula C3H8. It burns in air to produce carbon dioxide gas and water vapor. And the hint is you have to think of another gas that is required in order for something to burn. And that hint hopefully gets you to realize that the other reactant required for something to burn is actually O2 gas. So the first thing we're going to do is write a word equation for this chemical reaction. The first thing we have is propane. Oops. So we've got propane, which is a gas. So I'm going to practice writing states for all of the elements and compounds in these chemical reactions. Propane is going to react with oxygen, which is also a gas. It does require a special condition. So if we want something to ignite or we want something to burn, the special condition is some heat source, some ignition source to get things going. So our special condition is heat. This is going to produce carbon dioxide gas plus water. And the hint here is we're dealing with water vapor. Vapor is a gas. So there, that's the word equation. Next up, we're going to turn this into a skeleton equation. So all I'm going to do is write the same thing, but replace the names with formula. So propane is C3H8. That's a gas. Oxygen is a diatomic element, which means when it exists by itself, it exists as O2 gas. This reacts to form, with the help of heat, carbon dioxide, which is CO2 gas, and water vapor, which is H2O, also a gas. And that's it. Next question. Calcium is added to water, and when that happens, hydrogen gas is released and a solution of calcium hydroxide is formed. So for the word equation, we are starting with calcium. Calcium is a metal, and when metals exist by themselves, we just write the name. All the metals except mercury exist as solids at normal temperatures and pressures. So when calcium is added to water, our other reactant is water. Water is a liquid at standard room temperature and pressure. Hydrogen gas is formed, and calcium hydroxide is formed. Calcium hydroxide, you're going to have to go back to what you know about writing the name and formula for ionic compounds. That'll come later. Right now, I'm just going to write calcium hydroxide. This is an aqueous solution. How do I know that? Because it says a solution of calcium hydroxide, so aqueous solution AQ. Turning this into a skeleton equation, I've got calcium, which is a solid, plus water, H2O, which is a liquid, reacts to form hydrogen gas, which is H2. Why is it H2? Because hydrogen is another diatomic element, and we know that because of Hofbrinkel. And calcium hydroxide. Calcium as an ion has a charge of 2+, meaning it needs to get rid of 2 electrons. Hydroxide is a polyatomic ion with a charge of 1 negative. So that means we will create 2 hydroxides for every 1 calcium, CaOH2. And that's it. Last example. Aluminum metal combines with a solution of hydrochloric acid, HCl, and yields solid aluminum chloride plus hydrogen gas. A solution of means hydrochloric acid is an aqueous solution. So keep that in mind when we write our chemical reaction. Aluminum is just a metal at normal room temperature and pressure. It's going to combine with hydrochloric acid. This is a solution of hydrochloric acid, meaning it's AQ, an aqueous solution. This will form aluminum chloride, which is a solid, and hydrogen gas. Turning this into a skeleton equation, I've got aluminum plus HClAq reacts to form aluminum chloride. Aluminum will get rid of 3 electrons in order to become a stable ion. Every single chlorine ion will need to gain 1. So I'm going to need 3 chlorines for every 1 aluminum ion created. Hydrogen gas again is H2. And that's it. One final note before we end. If I were to measure the mass of all of the reactants and then measure the mass of all of the products in any chemical reaction, what do you think we would find? How would they compare? I want you to imagine you're taking into account every single atom from every single one of the reactants, and then you're taking into account every single atom from every single one of the products, and you're comparing them. When you compare all of the atoms you start with to all of the atoms that you end up with, you should have the same mass before and after. Why? Because atoms cannot be created or destroyed in a chemical reaction. The atoms that you start with in the reactants are exactly the same as the atoms you end up with in the products. So we should have a mass that is equal before and after. This idea can be represented by a chemical equation. If we were to take one of our skeleton equations and balance them, which just makes sure that we have the same number of atoms on each side of the chemical reaction, that would represent kind of what's happening in real life, that atoms cannot be created or destroyed. This is actually called the conservation of mass. Mass is conserved. So what we're going to do now, at the very, very end of this note, we're going to go back to our 3 examples, and all we're going to do is count the number of atoms on each side of our chemical equation and ask ourselves, is this chemical equation balanced yet? We won't balance anything today, but that's where we're heading in the next few lessons. So let's go back to example A. What I'm going to do to take into account all of the atoms on the left side and the right side of my equation is I'm just going to make a little chart. So on this chart, I'm going to write down all the different atoms that are present in this chemical reaction. I've got carbons, hydrogens, and oxygens. On the left-hand side of this chemical equation, I have a total of 3 carbons. I've got a total of 8 hydrogens, and I've got a total of 2 oxygens. On the right-hand side of my chemical equation, in my products, I've got a total of 1 carbon, 2 hydrogens, and 3 oxygens. 2 oxygens here, 1 oxygen here. So therefore, this is not balanced. I do not yet have the same number of atoms in my reactants as I do in my products. Next example, same thing. This time, I'm going to compare left-hand side, right-hand side with the atoms that are present, calcium, hydrogen, and oxygen. So on the left-hand side, I've got 1 calcium, I've got 2 hydrogens, and 1 oxygen. On the right-hand side in my products, I've got 1 calcium, I've got 4 hydrogen. 2 hydrogens are here. I've got 2 hydroxides. So I imagine like I'm distributing the 2 inside the brackets, meaning I've got 2 hydrogens and 2 oxygens in this compound here. So I've got 1, 2, 3, 4 of hydrogen, and I've got 2 oxygens. Therefore, this is also not yet balanced. Last example, the one with aluminum and hydrochloric acid. Left side, right side. The atoms that I'm dealing with are aluminum, hydrogen, and chlorine. On the left-hand side, I've got 1 aluminum, 1 hydrogen, and 1 chlorine. That's easy to add up. On the right-hand side, I've got 1 aluminum, 2 hydrogen, and 3 chlorine. So none of the examples we saw today are balanced. Like I said, we're not going to be balancing anything today. All we're doing is identifying whether or not these chemical equations are balanced. Are they reflective of the conservation of mass? Now for homework, which is the rest of your worksheet for today, you're given a bunch of sentences describing chemical reactions. For each of these, you are going to write down the word equation, the skeleton equation, and all you're going to do is add up the total number of atoms on the left and right-hand side and ask yourself, is this chemical equation balanced already? So it's exactly the same as the 3 examples we did together, except this time you're going to do these for homework and you're going to try them on your own.